Hello, everyone. My name is Emilio Martinez-Paneda, and I am an associate professor at the University of Oxford. I gave this talk a couple of weeks ago at the European Corrosion Congress, and there was significant interest in the talk, and a number of people have approached through email and after the talk asking for the slides and if we could share the transcript of the talk. So I decided to record this video so that everyone can access. And basically, as you can see, the aim of the talk is to discuss, whether hydrogen can be transported within the natural gas pipeline network, or more precisely, under which conditions will hydrogen transports fail? So can we map the conditions over which it's safe to transport hydrogen in an existing natural gas pipeline infrastructure? So this is basically the outcome of the outline of the talk. So I'll first discuss how we can use, I would say, state-of-the-art scientifically rigorous models to answer that question, to quantify under which conditions we can transport hydrogen in natural gas pipelines. And just for the sake of clarity, I will be discussing some of the inputs of the model, just to showcase that all these models rely purely on few parameters, and that those parameters are very well understood. So these are very rigorous mechanistic models. I'll then showcase how those models can deliver reliable predictions, how they benchmark very well against both lab experiments, but also full-scale tests. I think that's important. And then finally, I'll spend more time on the third point, discussing under which conditions can hydrogen be transported in natural gas pipelines. Can we use the state-of-the-art scientific models to predict when pipelines exposed to hydrogen gas will fail? And then I will start this discussion by looking at what industry is doing, what the transmission gas operators are considering, right? Are there fracture mechanics-based protocols that are using appropriate for this? Then I will discuss the limitations of those, and then discuss, whether suitable models can be used to understand the role of key variables such as defects, macrostructure, heat affected zone. And then finally, I will discuss whether the insight from these sophisticated models can be translated into simpler engineering tools. So let me start with the details of the model. Okay, we want to come up with a model that is mechanistic, that we can trust, that is as reliable as possible, to answer the question or to map the conditions under which hydrogen can be transported safely in natural gas pipeline infrastructure. So let me explain you a little bit of the ingredients of the model, and I'll do so by discussing each of the aspects involved in hydrogen embrittlement. So first, the ingress of hydrogen into the metal, then the diffusion of hydrogen within the metal and within the microstructure, and then finally the embrittlement process per se, the nucleation and growth of cracks due to the presence of hydrogen. And one thing that I want to emphasize here is that my philosophy here is to maximize the physics. There's no fitting parameters, there's no strong assumptions. I'm basically reproducing as much as I can, resolving the underlying physics, the physical processes that describe hydrogen embrittlement. So we want to minimize assumption, and we want to minimize parameters. This is a fitting parameter-free model. There's no fitting parameters here involved. So let me start with the hydrogen uptake stage. Of course, I'm focusing here purely on the case of gaseous environment. So for a hydrogen gas environment, where I know what is my hydrogen pressure, what is the amount of hydrogen that is coming into my metal? This is basically what I'm interested in. I think the good news here is that we have a well-established equation for this, a closed-form solution that is Siebert's law. And you can see it here, basically relates the hydrogen concentration, the lattice hydrogen concentration in the subsurface of the metal, to the pressure, or fugacity if you're dealing with very high pressures. But for the pressures that we will be discussing today, pressure is fine. So this is an input. We know what is the pressure of our gas. This is the characteristic of the environment. This is what we want to obtain. And what is here is the solubility of the material, which is a material property that we can measure. And the only thing to take into consideration is that this solubility is dependent on the hydrostatic stress. So you need some sort of finite element model to calculate the hydrostatic stress if you're interested in knowing what is the hydrogen uptake ahead of a defect. But otherwise, it's pretty straightforward. But again, I must emphasize that this is not negligible, because normally we measure this solubility using a permeation experiment. And in a permeation experiment, of course, the tensile conditions is an unloaded sample. So it's going to be very different to those ahead of cracks in a pipeline. So that's important. But we know what is the contribution of the hydrostatic stress, sigma H. You can see here that it's an exponential term. So this is going to magnify the impact of this hydrostatic stress. And as you can see, it has basically the gas constant, temperature, and the partial molar volume. So this we know, partial molar volume of hydrogen is this number here, and then all the other parameters we know. And the hydrostatic stress comes from a finite element simulation. So what do we need here, basically? What are the inputs of the model? So the model is able to predict the lattice hydrogen concentration as a function of the pressure of my gaseous environment. And then the only properties that come into play is the stress-free solubility. This is something that we know. It has been measured in the literature multiple times. The partial molar volume of hydrogen in the solid solution. So for BCC materials, we know again what's the number in there. There's no uncertainty here. And then, of course, because we need to calculate the hydrostatic stress, we need also a mechanical description. So we need, a Young's modulus, which we know what is the value for steels, Poisson ratio, yield stress, which we're going to consider various different type of pipeline steels with different yield stress, and then the strain hardening exponent, which is typically around 0.1 for this kind of pipeline steels. And then we need information from the environment, the hydrogen pressure, again, something that we know very well. And then, of course, we need also temperature, gas constant, and hydrostatic stress that you get from final elements. So there's really no fitting parameters or no uncertainty. We can quantitatively predict what is the hydrogen uptake in here. And then what are the model outputs? Well, the lattice hydrogen concentration in the surface, or surface of the metal. If you combine this with a trapping model, as I will discuss in the next slide, then you can also get the trap and total hydrogen concentrations in the subsurface. And there's a bit of discussion about the applicability of Sievert's law, but I think it's mostly a misunderstanding. It's related to the fact that, of course, when you measure hydrogen uptake, you typically measure the total hydrogen concentration. So you need a trapping model to distinguish lattice and trap. But for lattice hydrogen concentration, this is a well-established and rigorous expression. Okay, so once you know how much hydrogen is coming into your metal, then you need to quantify the distribution of hydrogen within the pipeline, within your component, and also within your microstructure. Because hydrogen not only travels freely through the crystal lattice, as you can see here, but it's also trapped, sequestered at microstructural defects such as grain boundaries, dislocations, and carbides. So there's a couple of ways of doing this. First, or one approach is to use effective diffusion models, which are based on an extended version of Fick's law. You can see here the concentration of hydrogen is driven by gradients of concentration and also by gradients of hydrostatic stress, again, and strong coupling with the mechanics part. And again, I'm highlighting in blue the material properties. As you can see, the only inputs the model needs are the diffusion coefficient, either lattice diffusion coefficient if you're modeling lattice diffusion, or the apparent or effective diffusion coefficient if you're looking at effective concentration, so diffusible hydrogen concentration. Again, these are two parameters that are very well known. There's no uncertainty here. We know what is the value of all the inputs of the model before we run the simulation. So there's no calibration, no fitting. Everything is pretty clear from the beginning. And then, of course, the partial molar volume. I'm not going to discuss the quantities that I've discussed before. And, of course, gas constant and temperature. And then we also need some boundary conditions, so some concentration of hydrogen in the subsurface, and that comes from the previous slide. So that comes from the gaseous hydrogen pressure and Sievert's law, and then the mechanical load. So whatever hydrostatic stresses you're applying, whatever load you're applying, that's going to result in a hydrostatic stress field. And then what do we get out of this model? Well, we get a distribution in time and space of the lattice or diffusible hydrogen contents. And then you have another model, which is a multi-trap model, which, for example, you could do it based on Oriani, or you could do it based on McNair-Foster. This is what you see based on Oriani. This is a situation where you're resolving the hydrogen distribution within the microstructural defects. So basically, you need these two properties in addition to the ones we discussed before: a trap density and a binding energy. Those will come from TDS experiments. And there's a little bit of uncertainty in there, but more or less, they're relatively well understood. And I think the good thing here is that because pipelines are exposed to hydrogen for a long time, we do get a steady state situation pretty quickly, after 2 or 3 days. And these pipes are going to be exposed to hydrogen for decades, right? So these values, even though there's a bit of uncertainty when it comes to extracting them from TDS analysis, there's a margin of error of 10, 20%. We don't really care because it's not going to have a role. We don't really care if the steady state is attained in 2 days or 2.5 days. And once you achieve the steady state, it's kind of the same distribution. But once you have these inputs into your material, once you consider this multi-trap model, then you can quantify the distributions in time and the space of the lattice, trap, and total hydrogen concentration, and then also, of course, the distribution of hydrogen within the microstructure. So this is a representative result. What you see here is a pipe that is being exposed progressively to a rising hydrogen pressure, pure hydrogen, and you can see how the hydrogen in the boundary increases, and you can also see how, as the time goes by, the hydrogen distribution within the pipe. So you see you have hydrogen coming in the inner part. This is a weld within the pipe, and then this hydrogen equal to 0. The hydrogen is free to leave the outer surface, so you get this gradient in hydrogen concentration. So this is the type of things that you can get with these models. Again, relying only on parameters that are very well understood, that have a clear physical meaning, and that we can independently measure with experiments. That takes me to the brittling part. So now I know how much hydrogen I have, where and when. I need to predict when cracks will nucleate and grow. For that, what we use is the so-called facial fracture models. And we use this for two reasons. The first one is that they're very computationally very robust. No matter what is the complexity of your cracking problem, whether you have 3D cracking problems, branching, coalescence, you can capture that and without any convergence issues. So it's computationally very compelling. But the other critical aspect is that it's physically sound because it's based on the thermodynamics of fracture, basically in a competition between the string energy and the fracture energy. This is a balance that was first proposed by Griffith and then extended by Orwan to elastoplastic solids. And basically you see the governing equation here. So it's a competition between the string energy density, the stored energy in the material that increases with mechanical straining. And whenever the energy stored in your material is large enough that it can be separate two new surfaces, can create two new surfaces, then you overcome this fracture energy and you see cracks growing. So again, based on thermodynamics, on this balance between stored and fracture energy, and relying on something that we know very well, is string energy density. It evolves with mechanical straining, and this fracture energy, that is the material toughness that we can measure in the fracture experiments. And I think the good point to emphasize is what I write here, because it's based on Griffith, because it's based on the thermodynamics of fracture, is in very good agreement with well-established fracture mechanics there. So you will see that in general, whenever we have homogeneous material under certain conditions, whenever we can, we should use fracture mechanics theory. It's well established. We know that it delivers a good agreement with experiments, and it is what is what that underpins our design codes and our standards. So it's good to have a tool that is in agreement with our standards, but I can also handle the more complicated scenarios where maybe conventional fracture mechanics or simple fracture mechanics models break down. And we have shown that this is the case not only theoretically from purely mathematical point of view, but also from a practical point of view. So if you run a finite element simulation with what is called a boundary layer model, where you prescribe a remote K, so basically, if cracking starts when G, the energy release rate, reaches a critical value, is the same thing as saying that cracking will start when the stress intensity factor reaches a critical value of the fracture toughness, right? So we know the relation between these two. So when you have a boundary layer, you can apply it a remote K, a remote J, and then you can see at what remote J cracking initiated. And since you're giving GC, or the fracture energy or toughness, as an input to the model, you can see if these two agree. And you can see here that basically, as to emphasize here, because we have a length scaling here that is connected to the strength of the material, I will discuss that later, your model is also mesh independent. So this is good because there's a lot of models out there which are mesh dependent, which means that, one engineer sitting next to the other one are going to get different results using the same parameters. So this is different. Here, as you can see, your response eventually when your mesh is fine enough, H is the characteristic element length. You see that as you refine your mesh, eventually you get the same behavior. So your mesh has to be fine enough. We see that 7 to 8 times, an element size that is 7 to 8 times smaller than the length scale. That's all we need. And once you have that sufficiently fine mesh, you get the same result. And what you see is that this same result that you get is precisely what you expect from fracture mechanics. So this ratio approaches 1, which means that cracking is initiating when your stress intensity factor is equal to your fracture toughness, or when your energy release rate is equal to your critical energy release rate. And as I said, the length scale also comes into play, and the length scale governs the strength of the material. There's a closed form expression for that, and therefore you are able to capture not only toughness dominated failures. This is, by the way, failure stress versus crack size, and you can see that we capture this well-known concept in fracture mechanics of the transition flow size that is widely used, for example, in standards such as the R6. So you go from toughness dominated failures, where again you can see a very good agreement with analytical predictions coming from linear elastic fracture mechanics, all the way to the situation where you get plastic collapse or strength dominated failures. So the model can naturally transition from one to the other because you're inputting as inputs the toughness and the strength of the material. And in fact, when you incorporate this, you can extend this model to fatigue. You can see here that we can define a fatigue degradation function that is basically a function that degrades your fracture energy with accumulating load in history. And when you do that, you can see that you get this kind of KT diagrams that are well known in fatigue. So as an output of the model, you can quantify those KT diagrams. You can calculate for both finite and infinite life. For as many cycles as you wish, you can determine what is this KT diagrams as an output of the model. So again, in very good agreement with well-established fracture and fatigue mechanics there. And this slide summarizes why these models have been so popular. These are all the outcome of simulations, some from our group, some from other groups. And you can see that over a wide range of materials, here we're dealing with metals, ceramics, composites, even functionally very materials, we can predict very nicely the output of experiments. And this is the output of very complicated experiments. So you can see that not only you can capture very complicated cracking phenomena, crack branching, nucleation of secondary cracks, coalescence of multiple cracks, but we can also do so showing a remarkable agreement experiments. So this is promising. So the method is computationally very compelling. It is based on fracture mechanics, and it delivers a very good agreement with experiments and with standards. So that's convenient. And if you want to extend that to hydrogen embrittlement, then the only thing you need to do is to model a three-field problem. This is the simplest one can do. So it's an equation for the formation of material, one for the hydrogen transport that I will discuss, and then one for the evolution of the damage in the phase field equation. And I'm highlighting here some of the couplings, but the key coupling, of course, is how hydrogen interacts with the toughness of the material. We know qualitatively what happens. Hydrogen reduces the fracture energy, but how to define this quantitatively is the key question. And we have proposed two approaches for this. Other groups have also built into our framework and proposed other approaches, but there's one more mechanistic, I would say, more academic, where you run atomistic calculations. These are DFT simulations now run by the Sintet guys on two types of grain boundaries in nickel. And you can see that, for a given trap occupancy, so interface occupancy could be grain boundary occupancy, you can come in here and reduce quantitatively the fracture energy. And see if you take, for example, an Oriani model, then you're able to quantify what is the reduction of fracture energy. But most often when we work with our industrial partners, we look for this phenomenological or empirical approach, because this is useful if you don't know anything about your material, but most often we're dealing, like here, with pipeline steels, where we have plenty of toughness versus hydrogen content data. You can see here, toughness, fracture energy versus hydrogen content. You can see there's plenty of data. This is from Sandia, I think. Most of the data is from Sandia, X80 and X52. So we can fit that data with a polynomial and introduce it directly into our model. So basically what this means is that at the end of the day, this model for embrittlement, the only input that has coming in is the toughness of the material, which is, you can get from the fracture test. For example, for plane stress, we know that it's equal to the fracture toughness to the power of 2 divided by the Young's modulus. The fracture strength, which comes into play in the model for the length scale. This is the closed form expression. So this is strength equals, as you can see, is a function of Young's modulus, fracture energy on length scale. And then we have this hydrogen degradation function, which can come from atomistics or from experiments on toughness versus hydrogen concentration. And this is the case I'm going to focus here today. I'm going to remove all the assumptions. I want to have everything that relies purely on experiments and on physical parameters. So again, there's no calibration parameters. There's nothing that we can play with. We know all the inputs before we run the calculations. And then what can we get out of these models? Well, the nucleation and growth of cracks for arbitrary choices of material properties, environment, and loading conditions. So let me show you then some representative results showing how those models can blindly predict the outcome of experiments. And then we will focus on our problem at hand, the pipeline problem. So you can see here a comparison with two pipeline steels. These are our curves, crack growth resistant curves. So these are the outcome of fracture experiments in air and in hydrogen. You can see this is an X80 and an X52 steels. And you can see that we get a very good agreement in terms of the J versus crack extension in both cases, for both materials. And again, with no fitting parameters whatsoever, there's no calibration here involved. And you can see that we predict very well what's happening in air. And then we introduce hydrogen into our samples by using Siebel's law and putting an appropriate boundary condition, and we capture very nicely what comes out of it. And we have also tested these materials across a wide range, these models across a wide range of materials. This is a comparison for high-strength steels. This is for duplex stainless steels. So everything here, you can see that we get a very good agreement experiment. These are pre-charged samples with notches. These are samples subjected to a constant load, where you can see that not only we get good agreement, but we can also run virtual experiments over very large timescales. And basically, you can do anything you want, right? So you can go down into the microstructure. This is, you can see a polycrystal. We can resolve the microstructure and rank different polycrystalline macrostructures and compare the susceptibility to hydrogen. These are cracks going in the macrostructure. But you can also handle complex, large-scale problems. This is a classic screw failure test. And you can see here, let me run this video. You can see here a very complicated problem. We have a pipe containing hundreds of defects due to pitting corrosion. And we can introduce those defects into the model, and we can see how those defects are growing. And then eventually, as you can see here, how you get the coalescence of multiple defects and the complete failure of the balance. So no matter how complicated your problem is, whether it's small, whether it's large, the model can handle it. And it can do so, showing, again, a very good agreement of experiments. So that's reassuring. And one last thing that I want to say is that the model also works very nicely for fatigue. And you can see here that, again, we have a fatigue degradation function. There's no additional coupling defined between the fatigue and the hydrogen. It's just both degrade the fracture energy. So there's no extra fitting parameters. And you can see that by doing that, we're able to get a very good agreement with virtual Essen curves, but also a very good agreement with fatigue crack growth rates. Here you can see data from Sandia have been obtained for different hydrogen pressures, for different load ratios, for different frequencies. And you can see that the model, we can do, this kind of virtual fatigue tests, and we can see the crack growth rates, and we can compare against experiments, and you can see that we get a very nice agreement. So for every condition that we consider, every different load ratio, frequency, pressure, whatever we threw to the model was able to predict. And I emphasize, there's no recalibration here involved. So the same model you're using for this result in air is the same one here. We just change the way we load our sample, whether we load faster or slower based on this frequency. We change the pressure using Sievert law. We change the concentration of hydrogen that we put on the surface. And then we change, of course, the loading ratio as well. So it's all playing with the loading conditions, but we are not touching any of the parameters involved in the model. So these are all very rigorous predictions. And more excitingly, we can also do things not only at the lab scale, but also at the full scale, right? We can benchmark our model against full-scale samples. So this is a comparison with some full-scale tests done on pressure vessels. Fatigue tests, where they consider 2 types of alloys and 2 types of defects in those pressure vessels. And as you can see, we get, again, a remarkable agreement in terms of cycles to failure. So we can simulate in 3D the pressure vessel. We can emulate exactly the conditions of the experiment. And as you can see, we get very nice agreement in terms of the number of cycles to failure across material and different notch geometries. And I guess the reason why I'm showing fatigue, I'm only going to be discussing fracture in the case of the pipelines, but the reason we're showing fatigue is that if you have a model that is able to predict fatigue in both, lab and full-scale tests, then, predicting fracture is kind of a toy problem. It's really straightforward. Okay, so let me get into the interesting part. So, okay, we have seen that the model is based on, physical parameters that are very well understood, that can be nicely and precisely measured in our labs, that have a clear physical meaning, that are known beforehand, so there's no calibration and uncertainty. And we've seen that this model is able to deliver a very good agreement with experiments across a wide range of materials, boundary value problems, fracture, fatigue, lab scale, full scale. So now the question is, okay, we have these models that we trust. What can we learn about those models when it comes to transporting hydrogen natural gas? But before I get into this, let me discuss what industry is doing, right? So how do we answer the question of, can existing natural gas pipelines be used to transport hydrogen gas? This is a complicated question to answer. Because, of course, first of all, the weakest link are clearly going to be the welds. And a point that I want to emphasize today is that we should always, of course, design based on the weakest link, right? In the worst case scenario. We don't want to design based on the most frequent case scenario, because that's not going to be the most challenging. We always need to understand very well what is the weakest, worst case scenario. And the weakest link are going to be the welds. And that's a problem because, of course, we are thinking about pipelines that have been deployed over decades, since the 50s. So we have an almost infinite combination of pipe material, weld condition, and also, of course, pre-existing defects within the assets, residual stresses, and also conditions that we are considering, right? We want to consider, different hydrogen gas purities, different pressures. So this is an almost infinite combination of all these things. So it's quite difficult to test in lab scale all these combinations. That's why I think models can be a key factor here. Again, welds are the weakest link, but they're very difficult to characterize, right? How do you introduce residual stress into your lab? How do you get sufficiently large samples along the heat-affected zone to do a proper fracture test to understand what is the fracture resistance of that heat-affected zone? There are multiple challenges associated with testing welds. And also, even if you try to do full-scale testing, which is, of course, very expensive, you have an iterating native oxide layer that can prevent hydrogen ingress over the 1-2 months where you're running your full scale test, but it won't prevent hydrogen ingress over the decades where you're going to run your pipeline. So it's a very complicated test it's a very complicated question to answer. And the key point is that this question cannot be answered purely with experiments. We need some sort of models. And this model, I think, is the closest you can get to the physics. Okay, so what is industry doing? This industry typically doesn't have access to this kind of sophisticated models. So what are the natural gas operators doing to assess whether their pipelines are ready to transport hydrogen? Well, I think the best ones, the ones that are more engaged in research, what they are doing is basically trying to solve this problem through a combination of spending a lot of money, gathering a lot of data, and using fracture mechanics. Because fracture mechanics, for homogeneous materials is rigorous and robust. So the problem with this, of course, is that you need a lot of data, because every time you change your mind about what hydrogen blend you want to try, or what hydrogen pressure you think you can handle, you need to run a very expensive experimental campaign, or you need to run experiments in hydrogen gases, where not everyone knows very well how to do their experiments properly, so there's some uncertainties in there. And the other issue, of course, is that once you gather all these data, you have basically a fracture toughness data. But what do you do with this fracture toughness data? Fracture toughness is something that you measure in an homogeneous sample. But the pipes, as you can see here, are not homogeneous. So the idea of, a K field, a stress intensity factor, a fracture toughness, those ideas of fracture mechanics work very well if you have an homogeneous sample. But at the moment you have an heterogeneous hydrogen distribution within your pipe, as you can see here, because we go from this region where you're in a region of the pipe where you're exposing your pipe to hydrogen to this outer region where the hydrogen is free to leave the pipe. The moment you have this kind of heterogeneous distribution, because of the sensitivity of the fracture toughness to the hydrogen content, you have basically an heterogeneous distribution of fracture properties. And then you no longer can apply fracture mechanics. So that's a challenge. So what is industry doing then? Okay, well, basically what they do is they assume the worst, so to say, right? So they assume that the only cracks that matter are the internal cracks, and that leaves a big if, because external cracks can also play a role, and that's something that is an ongoing discussion in the community. And then also they assume that the behavior is governed by crack tip conditions. So basically what they're assuming is that, instead of having this distribution of hydrogen, as it will happen in reality, they assume that the hydrogen is going to be all within the pipe distributed the same as in the inner surface. So, they say, okay, let's be conservative. We're going to distribute hydrogen like this. We're going to assume that our pipe is fully saturated with the hydrogen on the inside. Then we do a lot of experiments, expensive experiments, to quantify the hydrogen toughness for different, vintage pipes, different years of construction, and for whatever conditions I'm interested in. It could be, 3% hydrogen blend and a 90 bar hydrogen pressure. Then they get all this data from those labs, and then they say, okay, now I draw a line over here, and this is going to be my operating fracture toughness. So then I'm just going to compute my stress intensity factor, and I'm going to compare to this fracture toughness. And that's okay to a certain extent. I mean, I believe fracture mechanics. It is true that it's to a certain extent conservative, although not too much, because it makes sense that, inner cracks in principle, one would imagine to be the most critical ones. And in principle, one would imagine that everything will be governed by crack tip conditions. So it makes sense that the condition that actually matters, this one is not too far away from reality. The problem lies here, basically. The welds. So you have welds that are very heterogeneous material behavior. You have a stress discontinuity, you have hard spots. And you can see this here, right? This is the harness map provided by EPRI, our colleagues at EPRI. And you can see very significant changes. So you go from areas where you have a hardness of 140 to areas where you have a hardness that is above 240 Becker's hardness. I mean, these are significant differences. You're almost duplicating the hardness. And we know that hydrogen susceptibility is very sensitive to hardness. So that's a problem. You have very significant, this approach is fine if you have an homogeneous material, but you don't have an homogeneous material here. And so this is a challenge. It's also a challenge not only because you don't have an homogeneous material, but also because, as you see, you have basically a composite. You have jumps between heterogeneous material. That's going to create races in the stresses. That's going to create hard spots. So that's going to be quite challenging. Not only you need to understand these materials individually, but you need to understand how they behave together. And also, so basically, what does this mean for industry? Well, this means that either we need clever experiments that will allow us to determine how this heat-affected zone is going to behave, which is tricky. We're working on that, and I will update you on that front in the coming months. That is tricky. You need to characterize the fracture mechanics of that heat-affected zone, which is difficult. Or you need sophisticated models, right, that can tell you if you understand very well what happens in each of these points, what's going to happen when you put all those things together. So this is what I'm going to use now. I'm going to use these sophisticated models and give you an answer today. So how do these sophisticated models work? Well, it's the same model that I showed you before, but you combine with some welding process modeling. So you know what is the distribution of residual stresses, you know what is the distribution of your faces, and therefore you know what is their toughness distribution. And again, let me emphasize, the problem with industry is that this works well. The problem that industry is approaching is that this works well when you have an homogeneous material. So this works well if you're looking at the integrity of your base material. If you do this approach for the base material, then you're safe. But the problem is that the welds are going to fail before the base material, and this does not work in welds because, again, you have a heterogeneous material behavior, and you're not able to characterize what is the fracture toughness or the heat effect. So that's the challenge. So we hope to overcome this challenge by using this sophisticated model, so to say. So you have a simulation where you do the weld process modeling, and then you use this model I showed you before to predict the critical pressure at which the pipe will take. So this is the welding process simulation. There's an entire community devoted to welding process modeling, and they have very sophisticated tools, so they can do these things quite precisely. You can see here the simulation for a 2-pass seam weld, and here for a multiple-pass girth weld. And you can see that basically you simulate the welding process, and then you get a distribution of residual stresses, and then you get a distribution of the faces, of the different faces involved in your material. And we have seen that those distribution of faces, by the way, you can correlate those to hardness and deliver a very good agreement with the hardness maps that we have shown before. Once you do that, once you have your residual stress distribution and your material property distribution, then you expose your pipeline to a rising hydrogen pressure. And you can see that the hydrogen is increasing. And eventually, when you reach a critical hydrogen pressure, you will see that a crack grows. So you can quantify what is the critical hydrogen pressure at which your pipeline failed. So we have done this, and we published a paper on this. It was International Journal of Hydrogen Energy earlier this year, where we basically conducted multiple studies to try to, for example, systematically understand what was the effect of residual stresses, porosity that comes to the weld, but mostly pre-existing defects, right? We try to do a systematic study to understand various combinations that we know exist in those assets of pre-existing defects. And interestingly, we found that the flow that is 3 millimeters long and this alignal in the heat affected zone can deliver a critical pressure failure that is 15 megapascals, which is not too far away from very similar, from large-scale tests that have been done under very similar conditions. And this is problematic, of course, because these are some of the pressures that have been discussed to transport hydrogen, and this because we know that this type of flows exist in those natural gas pipelines. And again, you can test the role of macrostructural heterogeneity, and we can see a very significant reduction in critical pressure. So this matters. This has been neglected, but this matters quite a lot. And the other things you can do, of course, is that you can consider the conditions of the standard. So the standard will tell you under which conditions a weld was considered satisfactory. So a standard will tell you, okay, you are allowed to have a lack of fusion defect below 4 millimeters. You are allowed to have this kind of imperfections. You have to have this lack of penetration defects, root contraction, porosity conditions, undercutting. So you can introduce all of those conditions, and even assuming that the weld has been done perfectly in agreement with the standard, you can quantify what is the effect of each of those defects when it comes to reducing the critical pressure of your pipeline. So this is some of the things that you can learn from this sophisticated model. But more interesting, and I will finish with this, is that you can build failure assessment diagrams based on this sophisticated model. So you can plot, for example, what will happen in the case of this is, and this basically, let me clarify here. The failure assessment diagram with an updated toughness concentration is equivalent to what industry is doing with this fracture mechanics approach, right? So basically, a failure assessment diagram tells you that is this black line, and if you are below the black line, then you're safe, and if you're outside the black line, then you're unsafe. And what this means when comparing to your finite element model is that we're going to raise our basically in the x-axis you have the plastic collapse mechanism. So this is pressure versus yield pressure. In the y-axis you have the stress intensity factor versus the fracture toughness. And what industry is doing is basically trying to measure as precisely as possible this chop and substituting it here. So this is what industry is going to use. And when you do a sophisticated model, then you can drop points. You can plot points in this failure assessment diagram. And these are failure points, which means that if the point is in this area, this means that your failure assessment diagram is not appropriate, because your failure assessment diagram told me the model shouldn't fail, but the model failed. So let's see how the model works. First, we run simulations for homogeneous samples where we don't consider this heterogeneous distribution of properties that we find on the wells. And you can see that, you know, the predictions of the model agree quite well with the failure estimate diagram. So this is basically telling me that what industry is doing is fine if you are in the base material. So what industry is doing is trying to predict whether, you know, most of the pipes will, the behavior of most of the pipe. But of course, what we're interested in is what will fail first. And what will fail first is those wells. So what happens when we incorporate those heterogeneous samples? That's what happens. The model is telling you that the failures are going to happen much earlier. So you are sitting here thinking that you're playing safe, but actually because you are neglecting the complexity and the heterogeneous microstructure of those wells, this is basically what you're going to find, that your pipes are going to be failing much before you anticipated. But the good thing is that with these models, we can run this sophisticated model. So, you know, if you are capable of running those models, you can do so, and you can learn about, you know, residual stresses, defects, and so on. You can use it to guide inspections and so on. But even if you don't, you can use this model to run this virtual failure assessment diagram. This is some of the work that we're doing with EPRI. And then you can draw a new line here and, you know, quantify what is the safety factor that you need to do, that you need to apply to your standard fracture mechanics assessment because you are not considering these heterogeneous properties. So just to finish, I'll summarize by saying the only inputs that come into the model are the ones that you're seeing here. All are very well known and understood. I mean, if we don't understand these inputs, we cannot really work with standards because, you know, what do we have here? Fracture toughness, Young's modulus, Poisson ratio. We cannot quantify stress intensity factors if we don't know these numbers. So all of these parameters we know beforehand. There's no need for recalibrating them. We're not fitting anything. All of them are blind predictions. So in the mechanical side of things, we know we need Young's modulus, Poisson ratio, yield stress, strain hardening exponent. So basically a uniaxial stress strain curve. From the fracture perspective, we need the toughness, we need the strength, and we need the degradation of how the hydrogen degrades with hydrogen concentration, how the fracture toughness degrades with hydrogen concentration, hydrogen degradation function. So basically, fracture tests at different hydrogen concentrations. Then we need the stress-free solubility, which you can get from a permeation experiment, the partial molar volume. This is well known. The diffusion coefficient could be lattice or apparent diffusion coefficient. Optionally, if you want to resolve the traps, trap binding energy and density, these do not matter much in this application, and we can get them from TDS analysis. And then, of course, you need other things like the pressure from the environment and the temperature. But then once you have these inputs, which are very well known, then you basically have a physically based fit and parameter-free model based on these phasing methods that can not only answer technological and fundamental questions related to hydrogen uptake, transport, and embrittlement, but very precisely predict hydrogen-assisted fracture and fatigue, which is much more complicated in both lab and real-scale components. And when we apply these two pipelines, what we see is that we can quantify precisely under what conditions we can safely transport hydrogen natural gas pipelines. And this we can do through dedicated, cheap, and efficient virtual tests. So we can run experiments under, you know, different combinations of defects, of residual stresses, of weld and pipe materials, weld conditions. So we can try to understand what happens, for example, for external defects, internal defects. We can answer those questions, and we can use these tools to guide inspections, but we can also use these tools to come up with appropriate safety factors and failure assessment diagrams. And we have learned that we have shown that the approach that industry is doing is very dangerous because they are focusing on the most common scenario, but one has to design based on the worst case scenario, which is accounting for this heterogeneous distribution of the wells. And this is critical. And until we find a way of characterizing those heat-affected zones that we know are harder, more brittle, and much more susceptible to hydrogen embrittlement, we don't have a valid tool. So these tools can overcome this gap. These tools can help you quantify what is your safety factor in those problems. And that's all. I thank you all very much for your attention. I hope this was of interest. And of course, I need to thank all my sponsors and so on. And of course, once again, I emphasize that all our codes are freely available. So you can see that, you know, we're not hiding anything in the carpet. You can download our codes or rerun all the simulations that I showed you today at home and see that the numbers come as they do. Thank you so much for your attention.